everybody. Thank you all for coming to the next iteration of our Distinguished Speaker Series. Today's speaker is the esteemed Dr. Fred Oswald. He's a professor of industrial organizational psychology at Rice University. He received his PhD from the University of Minnesota in 1999. He's an international authority on personnel selection, college admissions, military selection and classification. He's also well known for his expertise on measure development, psychometrics, meta-analysis, impact analysis or adverse impact analysis, and big data analytics, which is the subject of his talk today. He's a fellow in Divisions 5, 8, and 14 of the APA, which is the Methods, Social Personality, and IO Psych divisions. He's known for critical reviews of the implicit association test, as well as of the 10,000 hours, right, the famous 10,000 hour rule of deliberate practice. This is also known as debunking fraudsters, which is one of his skills. He's been an editor at a number of high-profile journals, including the Journal of Management, Journal of Research and Personality, and Psych Methods, among several others. He is currently the past president of PSYOP, and was the president for the 2017-2018, the previous PSYOP conference. He has an H index, for those of you who are familiar, of 41, which means he's got at least 41 papers that have been cited at least 41 times, which is really good, particularly considering his age. It's really impressive.
41, no.
Right, when your H index is above your age, it's
right.
Yeah, so, just to give you a flavor of the heterogeneity with which Dr. Oswald has done research and the sort of topics that he's been centered around, I'm just going to read a few titles of some of his most influential papers. So one is titled The Mini IPIC Scales, Tiny Yet Effective Measures of the Big Five Factors of Personality. Another, Determinants, Detection, and Amelioration of Adverse Impact in Personnel Selection Procedures. Another, Predicting Ethnic and Racial Discrimination, a meta-analysis of IAT criterion studies. Applications of mean and covariance structure analysis, which sounds very technical, and I'm sure it is. Integrating correlational and experimental approaches. And lastly, Deliberate Practice, is that all it takes to become an expert? So I hope this gives you a sense of the caliber of scholar that we have here today to speak to us, and I'm really looking forward to his presentation. Please join me in welcoming Dr. Oswald.
Great, thanks. Thanks, y'all. Thanks for the warm welcome. It's really great to be here. I have to say, this has been a great visit already. I guess I'm at the halfway point now. And thanks to Ryan, who's been incredibly supportive since the get-go here when I was invited several months ago. I've been well fed, well watered and fed. The drinks have been pretty good. And I'm waiting, I guess, to be closed. Maybe there's some Hogan where I can get on the way out. And I've been well sheltered. The Tulsa Hyatt has been excellent. So really, thanks for your hospitality, and I've really enjoyed meeting you all. Hope to meet more of you after the talk. So today, I'm going to give you my perspectives or experience in working with big data, and big data is a moving target. It's an evolving field. Would I call myself an expert in anything? I think it's more about, I know something, I've thought about it a little bit, but I hope you'll take whatever I have to offer in the big data arena and make it yours, to the extent you're interested and want to follow up with your applications. And again, I'm happy to talk with you about where you might want to take your own interests. So I guess what I'm saying is I know enough to be dangerous. I know almost nothing about a lot of things, and that helps me connect the dots, in terms of being an editor or kind of a researcher with broader connections. So here we go with that in mind. What got me interested in big data, there were some obvious successes happening outside of our focus in terms of organizations. You see Jeopardy, where Ken Jennings plays IBM Watson and loses. And that is an amazing task, right? Because you're dealing with natural language processing in real time. So quite the amazing feat, not simply the effort of flipping a switch. A lot of teams, multiple teams working together to make that happen. AlphaGo, right, beats Sedol in multiple matches, and Lee Sedol, remarking on the matches afterward, was just amazed at the creativity that emerged from AI. Remarking that it seemed almost inspired and personified the experience, seemed human, a very, very good human. Then, following that chronologically was AlphaZero, another Google project, beating Stockfish, which was the go-to chess engine for analyzing moves. Stockfish itself can consistently beat top players in chess, world-class players, no problem. And yet, AlphaGo can do Stockfish 1 better. And I forget the actual record of wins and losses, but what I remember is that drawing is extremely common in chess tournaments when experts of equal levels play one another, right? It's kind of like, well, I was going to launch into IRT and discrimination and being at similar levels of ability, but sort of that idea that if you're consistently winning, then your theta level is much higher. And so AlphaZero's theta level is extremely high and won a lot of games, drew some, and I don't think lost any. Here, I'm just pointing out the idea of AI informing consumer preferences and moving more into businesses, right? And how, sort of from the bottom up, we can model what people's behaviors are over time. Whether you think of that in a static way, like people have different networks of, for me, guacamole is connected to beer pretty strongly, and for you, it might be wine and cheese or something like that. But those networks can change within you over time as well, right? And so being able to model those network dynamics and also kind of have a social network on top of that, if you're thinking families, that type of sophistication is attempted to be modeled in the consumer setting, and not just for an enjoyable intellectual reason, although I love those things. They've been doing it for money, it turns out. So we're entering that space. We know about Cambridge Analytica, right? The idea that human behaviors can be extracted from big data and used to some political advantage, potentially. Obviously, we know about that from the media and the ethical concerns that are brought out from those stories, and we think about how that might apply in our own arenas when we work with big data. So that's certainly on all of our radars, I think, as we move forward. And I will return to that later. And that was about the study. Let me go back. Am I going back? Yeah, from physical features. So yet another study trying to get into extracting characteristics of people from big data, in this case, video or pictures. But moving back from those accomplishments in the big data arena, a few years ago, I started reading stories about how big data can inform the business world. And what really kind of irked me were how reporters were paying little attention to my field. And I'm pretty selfish, so that's why I was irked about it. And why aren't you talking about IO psychology when you talk about the science and the data coming together to look at workplace phenomena? Instead, reporters were talking about workforce science. When big data meets HR and their practices, that's workforce science. So I really appreciate folks like you, and I try to do this myself, to go out to the media and say, look, here's what we do, here's what the science is about, and by the way, we've been doing this for a long time, and to get out there and be connected to these other networks. These folks who are well-intentioned, that have big data in hand, but they don't necessarily know about the lessons that we've learned and the expertise that actually becomes critical when you want to actually know what algorithms are doing and what to do with the algorithms when they're done. Yet another article here, a reporter saying, are we using data scientifically to make people decisions? And they say, not yet. Wow. So, and that was not too long ago. So people are somewhat clueless, and we need to keep giving those clues out as we are. So turning to the big data community, when we think about the techniques that are out there and useful for psychology or psychological applications, you'll hear these words like cross-validation. We know about that somewhat in the traditional statistical modeling. But then words like gradient boosted trees or support vector machines, we'll talk about some of these terms. But these terms have been around for 20 years, just as big data folks may not know what we've done for a century. We don't know what they've been doing in the big data arena for at least 20 years. So it really takes some communication to know what is to be offered from this grab bag of words that you see here. We see some attention in practice. We certainly see applications in computer science and economics, but in psychology, it's just starting to change, at least in the academic journals. And I would say that practice is always far ahead of what academics are even thinking about sometimes, scientific journals, but that indeed is changing, fortunately. So what I'm going to do is, well, first I'm going to bore you if you already know about big data analytics. I may bore you anyway, but I'm going to describe a couple of big data methods. One is called Lasso regression, and even if you've heard it before, maybe getting a different perspective is helpful. And I'll then just, it's better to give an example and then describe a philosophy to me rather than the other way around. Philosophies can be pretty abstract unless you give some examples. So I want to give an example of big data method, describe the philosophy that's underlying it. Then I'll give you another method. Oops, messed up again. I'll give you another method, and then I'll talk about implications of big data and what are the problems with big data. It's a black box, we've heard. You'll really appreciate how it's a black box when I describe these methods. So the idea is to go way beyond regression models, right? We like regression models because, hey, you have a ton of data, and now you can describe the data in terms of a slope and an intercept, right? So thousands of points are now described by two numbers. That ain't bad, right? But perhaps there's some more complexity in the data. Maybe we need more numbers to intelligently summarize the data and make use of the model that results in the future. But probably something like the graph on the right is too much, right? We're overfitting in that case. If you made a big deal out of the graph on the right, you're probably being too fancy, right? So we need something in between. Well, big data is trying to do that. And there are tons of methods. I got these numbers maybe 2 weeks ago, and they changed like the stock market. There's just tons of different black box big data methods that are out there and available through the R programming language. R has a package you may not know of. It's called Caret, and Caret is useful because it's sort of the bookkeeper for all the different methods that are out there in big data. It lets you compare methods on the same standard of how good are they in terms of prediction. It lets you manage the whole simulation process that's required essentially to judge a single big data method. It does multiple. It organizes the different simulations and lets you compare. So that's why that's a useful thing to mention here. The methods in general have a dichotomy that we all know is one is classification and the other, or prediction, and the other is a clustering method. So like, classification or prediction is where you have a criterion, right? You're either X or Y, or you have a continuous outcome. And then clustering is where you say, I don't know what there's no criterion. I'm just trying to figure out what kind of groups are what kind of lumps are in the oatmeal, so to speak. Right, and those are called unsupervised methods, whereas a prediction method is called a supervised method. The criterion, in a way, is supervising the goal of what you're supposed to do. So a variety of methods do one or the other or both. And not only that, you can combine different methods. So you don't have to say, I'm going to use Lasso or I'm going to use random forest. You can say, I'm going to get predictions out of a bunch of different methods. I'm agnostic to the method because nobody's told me which one is right. And I'm just going to average predictions coming out of it, and boom, that's going to be my prediction. And people often do that because there is no, if there were one right way to do it or a smaller number of right ways, you'd be hearing about it, right? Use this for that. And I could be wrong, but we generally don't see that. We do hear on the margins, we hear like, oh, random forest will give us a little more prediction than something else, than Lasso, which we'll talk about. But Lasso gives you a little more interpretation. Those things are important. But there's not, you know, the more general point is there are tons of black boxes and there's no one right way. So we're still exploring, we're still on the frontier. There's a picture of methods. Figured I'm giving a talk, I need to have a picture. So they cluster together in terms of relatedness. Yeah, no method is perfect. There's no free lunch. There's no one solution that's the best for all classes of problems, is what this slide is saying. And then I wanted to show you a lunch to make you laugh. And there we go. But let's jump to methods. And this is basically only math you'll see in this talk. So let's talk about Lasso. And I don't know if there's a laser here. I can pretend a laser's coming out here. So if you look at the math here, on the left is actually our friend linear regression, multiple linear regression. So minimize the sum of least square errors, right? May not be the way you've seen it before, but you kind of get the idea, right? You're squaring something, y minus the predicted value. So you have your data vector is x, and then your weight vector is your betas. So you're trying to minimize the squared discrepancies between the actual criterion values and your predicted values. So that's another way of showing it versus what you saw in Stat 101. But there's a new trick in town when it comes to the Lasso. The new trick is in red. And what it is to say, I'm not going to let you weight your variables like linear regression. I'm going to, if the weights are let's say it's a budget, okay? I'm going to give you a budget. If I give you no budget, you're like, well, great, I can't weight anything, right? Every predictor gets a 0. If I give you all the budget in the world, you say, well, I already know what's best. I need to accomplish the thing on the left side. The best is linear regression. Weren't you told like that gives you the highest R squared, right? Sample specific R squared. So what if I give you something in between? I say, I'm not going to give you the world so you can do linear regression. I'm not going to give you 0 because then you can't do any prediction. Let me give you a budget somewhere in between so that, well, what do we do in life when we have a limited budget? We try to spend our money wisely, right? And mathematically, we're doing that here. We're saying, well, if I have limited funds to weight my variables, I better weigh them wisely to try and get as close to this left side criterion, minimizing errors, as much as possible. But I need to put the weights in the right place. So this is the mathy magic that happens that lets you figure out how to spend your budget, is Lasso. You don't have to do it yourself, thank goodness, right? I couldn't do it by trial and error. But Lasso can. So I think there's a laser here. And oh, well, okay, all right, fair enough. So when you run a Lasso program, you might get output that looks something like what you see on the left here. And what the left is showing you is any vertical slice through that picture is a Lasso solution where you're weighting a set, some of the variables, okay? On the left side, see how all the lines converge to 0 on the left side? That means you have no budget, you can't weight any of the variables, right? On the right side, this is all normalized, it's going from 0 to 1. On the right side, you have the maximum budget. So the numbers you see there on the y-axis corresponding are the beta weights, or the least squares regression beta weights, So you've seen those before, you've done linear regression. If you run a linear regression, you're going to get what's on the right side, okay? In between is what happens when you start limiting your budget. Now, why would you do that? You like money, why would you limit your budget? Well, you're doing that because you're not trying to maximize prediction in your sample, you're trying to maximize prediction outside of your sample, right? That's one reason. So it turns out that giving up some maximal prediction in your model, it's bad for your single sample, but it's good for generalization. So shrink your budget to try and figure out generalization. Also shrink it because Lasso has a special property, which is Lasso does variable selection. It doesn't just do variable weighting. So selection, we know what variable selection means. It means you're in the model or you're not in the model, right? The predictor counts or it doesn't. So that means you weigh it in a sense, right? If you weigh it 0, you're out of the model, so it excludes it. And then it does weighting. It says, okay, if you're going to be in the model, do I give you the full-blown linear regression weight or do I give you something less? And you can see here, if you visually move from right to left, you'll see the linear regression weights are shrinking, right? They're all, if they're negative, they're going up towards 0. If they're positive, they're going down towards 0. They're not flopping around all over the place. Basically, it's saying if I shrink the budget, I'm shrinking all the weights towards 0. And eventually, I'm going to get to some points where certain variables drop out. So if you want to think about this graph in terms of variable importance, you'd say, well, when I go from no budget to something, see the purple there and the orange on the right? I mean, going up, right? Those seem to be the most important. As soon as I give you any budget, they're saying I'm in, count me in. So that might be some index of variable importance in a way. Are we good so far? And now we're going to ask, well, okay, Fred, you ran like 1 billion different models here. Which one should I pick? And the one you should pick is the one that gives you the best prediction in fresh data, essentially, in data you held out, right? And does that with weights that are going to basically have a stable solution, right? Oh. Well, I can, this might help. So go ahead and ask, and then let's see if your answer's up here.
Can you go to the previous slide?
Yeah, sure.
So as we're moving towards the right side of the graph, there's 3 lines that drop off real quick. Part of it drop off partway through. I can't tell the version back here, but suddenly that one drops all the way down.
Oh, down to like large weights?
Yes, yeah, I'm sorry, yes. So it suddenly gains a large weight, but it came in later than other variables that don't ever gain as much weight.
Yeah, yeah. Yeah, good. Yeah, it's a shared variance deal. It's like the variable was unimportant, but then other variables drop in, and now that variable says, I want to play too now, right? It got excited. So, yeah. No, that's really important. And I've thought about things like, I don't know, there may be some in literature on this, but I've thought about things like, sort of like the timing, but like if you look at the change, right, the derivative, basically, what's the rate of change as something enters? I think that maybe would tell you something, but I can't tell you today. But that intuition, I think, is really important. And from a practical point of view, it might be to say, we're always balancing statistics with our practical situations and intuitions, right? And if a company said, I can measure 100 things for your research purposes, but ultimately I can only pick 5, which 5 do I pick? Something like this might tell you, and you say, look, we're not maximizing prediction in terms of in sample, we want robust. We're also not maximizing even in terms of the most generalizable because we don't have time to measure everything there. We're going to go to a simpler model that still does the best we can, and this could inform that. So this is basically telling you what I told you, which I guess is a good strategy in giving talks, right? But so least angle regression is the kind of phrase you want to know when you see these pictures. Least angle regression is giving you all the possible Lasso solutions when you have no budget on the left versus ordinary least squares on the right. That's what OLS is there. So it's giving you that and everything in between. And then I just put construct labels on these saying, well, what if this was anxiety predicting performance evaluation? Or what if this was absenteeism rates predicting performance evaluation? I actually I took a correlation matrix out of personnel psychology and ran it through here, assuming the data were nicely behaved and stuff, but that's not the case. I'll give you these slides and you can review this later, but this is basically explaining what you just saw is, how did these Lasso solutions happen? You're basically entering variables partially until other variables, like I said, kind of get excited, basically. You're basically entering a variable in partially by raising the weight, looking at the residuals of the regression, and then seeing whether other variables that could enter the model outcompete that variable. And once that happens, then you start entering that variable as well. And how do you raise the weights? They're all moving toward their least squares solutions in a multivariate space. So save that for later. Even my eyes are glazing over. And instead, let's turn to what is going on as these models are being developed. And what is going on is cross-validation. So while you're developing a model, you're creating a model, deciding what the weights are, but you are holding out some data so that once you develop the model and its weights, you can take the data that did not participate in developing the model and get predicted values. Does that make sense? So that way it didn't bias, it didn't influence what the model was, right? And so those are kind of better, truer, the kinds of predictions you want in the real world. You want to be able to predict outside of the data you use to develop the models. So in the big data field, there are kind of two phrases we use. We use a training data set, which is used to develop models, and then we have a test set, which is the data you held out so that you're testing the model and putting those data in to see what the predicted values are. So training and testing is a very important distinction in big data. And that's the idea behind cross-validation, right? In our traditional regression analyses, there's a literature in JP on cross-validation. It's all about this. It's all about what's our prediction, what would our prediction be in data that didn't participate in developing the model in the first place. Of course, you want the sample to be somewhat similar, right? You don't want to test it on employees and then your holdout sample is Boy Scouts, right? That might be problematic, but you want it to be similar. You don't do this just once in the big data context. So let me just hold this up here. I think what I'll do, so often, and this is just a rule of thumb, but often big data folks will say, I did 10-fold cross-validation. Why 10? I don't know. But for me, it's useful because I have 10 fingers and I can describe it. Well, thumbs are fingers, right? Yeah. Okay. And then once you develop, take the 1/10 you have of the data becomes a holdout across 10 different models. So every data point eventually gets predicted values, right? And then you can see what the overall R-squared is, right? You could do that now. You just correlate your predicted values with the actual values of Y, and that'll give you an R-squared that, those 10 models were participating in. Now, there are fancier variations. You could say, well, I don't know if 10 is right. What if, I don't know. So let's do it again. Let's do another random sample and repeat the procedure. Now everyone has 2 predicted values. I'm just going to average them, right? So you could do that if you were staying up at night wondering whether the 10 splits you did before were actually the right ones or something like that, right? You can repeat the process all you want. So that's all that this slide is saying. And that is a really common, that is what big data does essentially, is cross-validation is at the heart. No matter what the black box is, that's what big data methods are doing when they cross-validate. So that's what's happening with the least angle regression graph you saw. Every vertical slice is a model, right? And every model is being cross-validated in this way. Why? Well, because now imagine this is essentially what you saw before. I should have flipped it. In the graph you saw before, there were 0 variables on the left and all variables were on the right. So sorry, I reversed it here. But it shows when all variables are in the model, your errors are low. But, and you can see that from the dual axis here. But actually, you don't lose much in terms of error, even when you go like to 8 variables in the model, you drop 4. And that's what R, the programming language here, settles on. There's a rule of thumb in big data and in the R program where you take the solution that has, your eyes can't tell you this here, but this happens to be the one with the lowest error. And then you go one standard error higher than that, and you accept that solution. And the reason is kind of the spirit driving that rule is error on the side of a little more error because you never know what your new sample is going to be like. So just be more conservative in that way, and also be conservative in that you might as well have a little more parsimonious model, right? Science prefers parsimony. Practically speaking, it takes less time to get measures, so let that factor into this as well. But I'd be the first to admit this is a total rule of thumb. It wasn't written on a gold tablet or anything. Okay, well, a quick extension of Lasso is called Elastic Net. And I'll just do this really quickly because we're going to go through random forests. Elastic Net is an extension that says if predictors are correlated and they predict a criterion, let them all participate in the model. Like instead of just picking one and giving that a weight, which is what you do in Lasso, for Elastic Net, what you do is say, hey, you two, you are correlated, you both get to play, and I'm going to share some of the weight with you all. You have to split it. You both can play, but you have to split. So Elastic Net is doing that. It kind of makes sense in psychology sometimes, right? Because conceptually, our stuff has a lot of positive correlations. But you do give up on parsimony then, right? So in Elastic Net, more variables are going to be in your model because if they're correlated, they're going to be allowed to play. And so that's the trade-off. Elastic Net incorporates Lasso, which you see on the very right, which is the variable selection, but then it incorporates ridge regression, which you may have heard of. Ridge regression is what makes what I just described happen. It makes correlated variables play in the model. Ridge regression goes way back. Ridge regression is, in psychology, we see it in the 60s, and the idea of ridge regression is the idea that drives big data today, and it's to say, I'm willing to come up with regression weights that are biased, meaning they're not the population values on average across random samples. I'm going to let them be a little biased because they end up being more stable. The weights are more stable. They don't flip around as much. And so that's the idea here is they're gonna, all of these methods in big data are doing that. They're saying, I'm willing to accept some bias in my weights as long as prediction becomes more stable. All right, so we now have learned a method, right? We learned a method about how to develop a model, how to choose between different models, right? So one thing you may have appreciated is that typically we run one regression model, report those results, right? Here we ran tons of models and chose the model that seemed to work the best, right? So we had a range of models. That's a signature of big data. And then we also worried about, we didn't just run a range of models, we did cross-validation. And that's another signature of big data. So you just went through some very basic important principles of big data. No matter what methods you're going to use in your predictive toolbox, those things are going to be driving what you're doing. And you'll see that as we go through the random forest method. But just to repeat the philosophy here, we developed a model on a training set. We tried to minimize predictions in a test set, right, by holdout data using the cross-validation approach that I described, where all data eventually becomes a test set in that 1/10 that you're holding out. So traditional methods are just capitalizing on samples, right? You run it on a sample, and even if it's a big sample, you might worry about some generalization possibilities. And actually with Hogan data, there may be some options where you can do some stratified random sampling where you're cross-validating in a more sophisticated way. That might be something we can talk about after the talk. But in traditional models and lots of things we read in our journals, I think we could worry about how generalizable those results are from a statistical perspective, certainly conceptual perspective. I think I'll skip these slides. I've already talked about this idea that we're willing to accept some bias as long as our variance goes down, as long as the variability in prediction goes down. I guess I'll give you this slide if you haven't seen it before. So the idea of big data prediction is that, ideally we would have the upper left. We're always on target when we're making predictions. We really don't want the bottom right? You're not on target, you're not even close to where you need to be. That's pretty bad. In traditional models, we might say the lower left is okay. Like, any individual estimate is going to be in a different place, but on average, we're going to be right. We're going to be correct, right, in the bottom left. There are a lot of statistics jokes there somewhere, right? Like you shoot somebody to the left and then to the right of them, and if you're a statistician, you think you killed them or something. Like, it's that kind of idea. So in traditional models, that seems to be okay. In the upper right, that's more like big data notion. There we're saying, yes, I know I'm off. I know as I engineered my problem to be off, but I know where I'm going to be, and maybe from a practical standpoint, that's not too bad, right? Versus the lower left, where yeah, I'm right on average, but I'm never exactly that close. So that's the idea, is a willingness to be wrong in the particulars of the weights, but to be more correct in terms of the goal you're really focused on, which is prediction. And by the way, that's one of the problems of big data, is we're worried about prediction at the expense of some understanding. And we'll get to that notion later. I don't have a timer, so I don't know how I'm doing on time. 20 minutes? Okay, good. Let me skip some math here. And let me just say, maybe I'll do this. Let's stick to this one. So big data analyses, like figuring out the right Lasso model, is about navigating what's called the bias-variance tradeoff. So in terms of that dartboard, where should we be in those quadrants? Well, big data methods are kind of navigating those, is saying, how much more bias can I give these weights and still get reasonable prediction, reduce the variance of prediction, and be more right than wrong in terms of prediction. So you're kind of navigating those dartboards. And what you're doing here is basically you're trying to trade off model overfit, which I've been harping on is bad, but model underfit is also bad as well, right? So, turns out you need to be conscientious at work. And you have a selection model that doesn't include measures of conscientiousness or measures that correlate with it that reasonably well. Well, you might be selling yourself short in the math and in terms of what you're offering to the organization, right? So in that sense, you're under-predicting, right? You're underfitting a model because there are variables that are important and responsible for the outcome, and you're not including them, right? That's model underfit. So in a big data approach, as you're navigating huge data sets, you're kind of saying, well, should I include this? Should I include that? I don't want to exclude something that's going to be important. That's the underfit notion. And if I exclude, that's where I get the left square. That's where I get bias. I'm biased downward because I'm underfitting. But if I overfit, if I say everything's important, look how high the R squared is. If I keep putting variables in, R squared goes up. I'm just going to keep doing that because it just keeps going up. It's exciting. Now I'm going to break for lunch and come back, put more variables in. But you're overfitting, right? As soon as you validate that model or get that model tested in fresh data, your R squared goes away, and you're sad. And so you You don't want to overfit, you don't want to underfit. And then life has a lot of the right. Error that you can't predict, right? Sometimes clients don't understand that, but sometimes they do, and they're telling you in ways that you're not thinking about in terms of the psychometric model. But you know, there are some things in the world that are conducive to outcomes. You might even know they exist, but you can't measure everybody on that, and you can't develop a model for it. You're going to have to chalk it up to error, right? And then there's some mysteries that are yet to be solved in terms of our science and practice, and for now that goes into error. So that we can't do anything about, but we can do a lot about bias and variance in the big data world. And this is my layperson's description. When people say, hey, I still don't get what you say, I say, okay, well, let me tell you a story. Let's say I was selling gloves, and my first step for selling gloves was to say, the best gloves are the ones that are custom made, so I'm going to sell you this glove that is it's custom made to my hand. It's awesome. When I put it on, it is great, so I'm going to sell a bunch of those. Nobody wants it because it doesn't fit their hand. Fit my hand, great, right? But I'm not a normal person, so it doesn't fit their hand. Okay, so you're upset by the lack of sales, and you go back to the cutting board, I guess, and you say, look, I'm gonna, you know, in a rage, you say, well, I'm gonna create a glove everyone can wear. It's called a mitten, right? Mittens work, they keep you warm. Your hands will definitely fit. I'm gonna try and sell that. Well, no one likes that either, right? Because you lost the functionality of what was intended, right? You can't move your fingers independently. So then you're going to go just right in the middle, right? Just right is to say I'm going to create gloves with fingers that fit most people, and that'll do the best job. So that really is the job of big data, is to find that middle model that doesn't overfit, right? So the glove is the model and the hand is your data, right? So the glove shouldn't overfit your hand, and it shouldn't underfit your hand either. So there's the layperson's explanation. Hold your applause, and we'll move on to another method. All right, so let's talk about another big data method that's entirely different. Entirely different, except that we are cross-validating, we are exploring for trying to get the best prediction and not overfitting our models. We're still doing that. So for random forests, what you can see here is we are building trees. Got to have trees. And we're building trees out of our set of predictors based on an outcome. And how do we do that? Well, what we're going to do, assuming we have big data here, is we have a bunch of data. We're going to pull some variables out of our grab bag. And just as a default value, if p is the number of variables, you'll take the square root of p. Okay, 100 variables, you take 10. Those 10 are your candidate variables at any branch of a tree. Okay, so at a branch of a tree, you pick one, and then you say, I'm going to put a cutoff in there between the red arrow and the green arrow, right? There's going to be a cutoff. Where am I going to put that cutoff? You're going to put the cutoff in a place that maximizes the mean difference on the outcome. So it's sort of like it's like a create your own ANOVA, right? So like at the node, at the beginning here, you have cognitive ability. You say, okay, here comes out cognitive ability. I'm going to create two groups, a high group and a low group. Well, create your own ANOVA. How are you going to do that? I'm going to put the cutoff on cognitive ability in a place that makes the mean of the high group maximally different from the mean of the low group. That's where it's going to go, okay? And then you do it again. You grab variables at random, you pick one, and you say, okay, well, now we're going to do conscientiousness. And the same rule, except it's going to be on the subset of data at that branch of the tree, right? You already cut the data into two parts here. Now you're going to take one part of the data with their criterion scores and play the same game with conscientiousness. Create a cutoff that maximizes the mean difference at that branch of the tree. And so there's a depth rule, like you can change the depth rule in R. You can say I'm going to stop at 3, or whatever, or you can make them deeper. But the deeper you make them, the more you're going to overfit your model to the data. You see how there's that trade-off again? So there's a trade-off between like the depth of the trees and the number of trees, how many trees, right? You could have fewer trees that go deeper, and that would be one way to predict the data. Or you could have lots of trees that are shallow. And actually, that's the way we tend to go. Lots that are shallow. And by the way, from a computational perspective, that's nice because if the trees are shallow, that means I can assign them to separate computers or separate cores of a chip, right? Because I don't have to wait. If I have a deep tree, I have to wait on all the prior levels to get to the deeper levels. If I have shallow trees, I can just give them out to anyone. I can give them to your iPhones and then have them send back the results to me, and it would all come into one place. So that's the idea, but that's just one tree. And oh, I forgot to tell you something. We created this tree off of a bootstrap sample of data. So you know bootstrapping is sampling with replacement. It's like if I have a sample size of 1,000, then I sample 1,000 cases, but some cases are going to be repeated and some cases aren't going to be sampled at all, right? That's what bootstrapping is. So you're going to have 1,000, but some cases are not going to participate in the model development because they weren't selected for the bootstrap. Well, guess what they get to do? The cases that didn't participate in the tree, they get to get run through the tree afterward. So on average, bar trivia, about a third of a sample doesn't get sampled in a bootstrap. It's called like the 68% rule. 68% of the data gets sampled and the remaining 32 sit out on average, right? Sometimes it's higher, sometimes it's lower. So that means every time about 32% of the data that didn't participate in the model development get run through the tree and they get a predicted score. So imagine you keep developing trees like this, right? Because you're building a forest. So you keep selecting variables at random at each node of a tree. So you're developing a diverse range of trees. You're getting a diverse range of predictions, right? And oh, what if a case goes through multiple trees? Well, that is going to be the case. They go through every tree that it didn't participate in developing, right? So a case might have, 1,000 predicted values because there are 1,000 trees that it didn't participate in its development. So what do? You just average them. You say, some trees are good, some trees are bad for every case. I don't know which tree is good. There's value in the average. So I'm going to walk through some slides that describe all this. So you're building trees. They're all different. This took me about 6 weeks to create right here. Because they are different, by the way. I'd use a microscope. And they each create different types of predicted values for the cases, okay? And you do that because it's better to have diversity. I mean, if I created trees that had the same prediction every time, why would I ever create 1,000 of them, right? It'd be totally redundant. So you want the trees to be diverse. Each tree is contributing a different prediction. And I have this here in a table form because we all like data tables. So here are cases, and then you see where they have predicted values. If the case actually was involved in tree development, you don't get a predicted value. If the case was not involved in the tree, then you run it through the tree and you get a predicted value. And then across all the trees, you see how many predicted values each case has, and they're going to vary, right? Because the bootstrap sample is random, they're going to vary. But if you run tons of trees, it's not uncommon to run like 1,000, 10,000 trees or something because they're fast. Then you average across the predicted values and get that prediction. Now you could say, I'd be curious, like what about the variation in predictors for a case? Does that tell you something about the case? Differences in variability across cases. I haven't really thought that through, but I think that would be an interesting question to pursue. Or flip it around and say, what about the trees that give more or less consistent predictions? So anyway. So the idea behind random forests is model diversity. And like I said, you don't want trees to give the same predicted value. That'd be on the left. You want to have diversity here. So you have the same trees on the left. This was a PowerPoint challenge for me as well. And you have diverse trees on the right. And that you want the power of that diversity to help you in prediction. So I hope you see here, even though Lasso and random forests were entirely different, that the same principles were developed, weren't they? didn't we? We kind of pursued different models, right? For Lasso, we tried different types of predictors going in there to see what happened. Same thing for random forests. We're trying all the variables and all these combinations and just seeing each tree as a model. Which one, not really one, which ones work as we look at the aggregate of the random forest. And we're always looking at cross validity. We're not happy with sample specific prediction. All right, in the interest of time, we're probably down to what, 10? 8, okay, give or take. Confidence interval, please. Let me just say this, like we've looked at generalizability in terms of cross-validation. We looked at model uncertainty because we changed our models all the time. We perturbed the data, not just the models, right? We perturbed the models in terms of like the trees and the forests. We also perturbed the data in terms of bootstrapping. So there's a lot of perturbing going on to try and figure out where's the stable predictive relationships in this mess. And by the way, we haven't even talked about like, what if the data are multi-level, or what if there's missing data, right? And these programs have some problems with that, and there's a whole nother kind of thinking you have to do to get your data ready for these sorts of analyses. Happy to talk with you about that too. But I think these exploratory approaches can give you at least some potential for hybrid analyses that you might have more top-down structural equation modeling, factor analysis, regression, et cetera. And you might still pay attention to cross-validation there. And it's very top-down, relatively theory-driven or experience-driven. But then here's some bottom-up, right? You might have some big data, some kind of more incidental or unstructured data, and you try and figure out a useful way to do prediction from that. So that's a useful complement in our field anyway, if not for particular projects. For our field, we need this, and it gives us opportunity to communicate with computer scientists and so on. This picture gives me some heart that, like I said, there was a black box of tons of methods, and I draw this figure out to say that, here are like 4 different black box methods, and they're yielding very similar solutions. So in terms of the overall decisions you have to make, you often get at similar values. When they disagree, it's usually about cases that are inherently hard to predict anyway, where no method is going to reign supreme. So it's useful to try the simple learners first. I'm quoting from an author here, upper right. Sophisticated learners are seductive, but they're harder to use. So I'd say, give big data a chance, dip your toe in the water, see if it offers you some increment over traditional methods. But these methods show you, like the simple models, like the trees, can give you something than something you might think is theory-driven, potentially. It's always a competition, I guess. Since we're running out of time, I want to point out here that, in my experience with big data, I have thought about our traditional models that are, I would call more intentional, right? We give the data to customers and our clients, and they're theory-driven. The folks engaging in the tests know what they're doing. They know what they're taking and why at some level, versus data that you're getting like video surveillance data or audio data, right? That's more incidental. It has more ethical issues potentially, right? And we can still develop predictive models, but that's a very different world. It's different analytically, it's different in terms of ethics, and so that distinction is really, I think, interesting. And we can make, one thing that's interesting in that world is that we can make our incidental data more intentional data through iteration, like through, we learn from big data analyses and we say, hey, look, here's a signal in the noise. And it's not a full-blown signal, it's just something we detected. We think we can interpret it, we're not sure. But that gives us opportunity then to say, well, if you're not sure, make that signal larger by developing a traditional measure. I didn't know that video, that video showed some negative team interactions, and here's why I think that's the case. Well, maybe you can then turn that. You found the prediction in the video big data, you structured the problem, and empirically it holds up. But can you turn that into a better, richer measure and test your hypotheses then from top down? So top down and bottom up are constantly able to interact, and you don't just do big data and stop. And that's what I'm saying here. This picture gets cited all the time since 1996, and my own addition here is to take the, you start with a silo of data on the left and you end up with a Dorito of knowledge on the right. And you can bring Doritos back to the silo. You can take your knowledge and create new knowledge, create new tests, generate more data from your new tests, and then get to knowledge again and keep cycling. And so I think that's an important part of this big data, is it's part of a broader cycle. I really should mention this because we are psychologically minded at heart, is that in the big data world, we often may think of anything as a predictor, whatever's on the hard drive, the items, the signals of behavior, right? The indicators. We might have millions of these. In psychology, we group them, right? We're construct driven, so we think about how these things might be related, and then we use data to test whether our clusters are supported. The big data world often may stick at the item level. Now, there are data reduction methods like factor analysis or principal components analysis that can extract clusters and then use those for prediction, but it leans toward the prediction and the black box notion that we're just trying to improve prediction. It doesn't go to the construct end of things, or forget about constructs even. It doesn't go to the interpretability notion. What if you had to go to court and justify how random forests were used to analyze video data and make decisions about someone's performance, right? We haven't tested that in litigation, but I would suspect a lot of that is, as I explained the method to you, there's a lot of black box there, right? You didn't measure the performance from a top-down approach with tied to a job analysis or anything like that. And so the top-down and bottom-up is iterating not only intellectually, as I mentioned with the Dorito of knowledge, but also with our how this plays out in organizations and in courts and so on. So I wanted to bring that out. It really goes back to our principles of measurement. So when I teach psychometrics, I bring out this Venn diagram all the time, much to the joy of grad students far and wide. And that is to say that we need to think about what we're measuring, that we want to cover what's relevant. We don't want to contaminate our measures, like we don't want to impose a high language requirement if we're not measuring language ability, right? And we don't want to not measure things that we should. That's the hardest thing. It's hard to see what's not on the page, right? It's really hard. Now you can consult theory and look at your measure and say, hey, there are gaps. That's one way to go about it. But it can be very hard to see that your measure is deficient. Chromebox alpha is not going to tell you that, right? It's more a conceptual issue. Contamination you might be able to get to statistically, but deficiency would be hard to. So those issues I think really come into play in the big data era as well, where you're playing with variables and indicators, but you're not necessarily thinking about constructs and theories and reasons and goals beyond just prediction. So I think that's really important. I'll just leave it there. Are we about up on time? I'll say that the military is trying to improve the explainability of these black box models. This is a not atypical military type of graph that there's lots of fanciness here, but the point of it is to say there's a black box of all kinds of big data methods, and they're investing in improving, moving from orange to green, moving from prediction over to getting their methods more explainable. Millions of dollars. This is a couple years ago they were starting on this. I'm not sure where they are, but we are in the same boat. And I guess that's where I'll leave us. I'll share the slides with you all so you can enjoy them on your own and ask me any questions. Big data has the opportunity, I think, to bring together different functions of an organization because, I mean, kind of like saying free beer, right? Lots of people show up. If you say big data, I think lots of people show up. And when they're connected to sources of data and you can talk to each other and form an analysis problem, I think that's really exciting for application and even for science as we try to bridge micro functions and macro functions of an organization. So thanks for having me. Happy to answer questions here or afterward. You can reach me at Oswald at Rice. And you don't see it there because I didn't finish apparently, but I have a website, workforce.rice.edu, and you can explore there too. So thanks a lot. I really appreciate it. This was fun. Yeah.
This is kind of a naive question, but how big does the sample have to be for it to be a big data sample?
Yeah, well, it's a naive question, but it's a good question. Big data, so the sample size can be anything. Big data will apply the brakes when it sees that you don't have enough data to support any complex relationships. So you can have a typical sample for a regression model, put it into big data, and essentially get regression results, right? But big data can also deal with something that regression models cannot, and that is when the number of variables exceeds the sample size. So if you try to do that in a regression, the matrix won't invert and you get an error. You can't run it. But in big data, even with ridge regression, but with these fancier methods, you can get all the variables to participate, right? So it is an important question. And then there's also what about big data where you have intensive experience sampling data, right, within smaller periods of time, and then you have broader HR data that's also big data, and how do you merge those? I mean, that's an analytic nightmare or opportunity, however you look at it. So,
I have another question.
yeah.
How do you model interactions?
So interactions are, well, there are a couple ways to answer that. So one is, for random forests, interactions are built in there. Very complex interactions that no polynomial regression is going to pick up on, right? And you don't even know what they are because even within models, you have these cutoff points and variables can get reintroduced into the tree. But then when you average across trees and their cutoffs and everything, you're like, what did I just do? I don't even know where the interactions exist. You can know how responsible a variable plays in all the trees. There are methods for, you can, instead of using that variable across these trees, you can say, I'm going to take you out and I'm going to put in a random variable, random noise. And if the trees degrade in their performance in terms of prediction, then that variable must have been important. If the prediction didn't change when you remove the variable, it must not have mattered. It's sort of like alpha if item deleted. It's sort of the same idea. So that's one answer. Another answer is in the Lasso model, which uses regression weights, you can enter interactions in there. So that it's called a group lasso, and pardon? Yeah, product terms and squares. And what it does is it enforces the main effects being in there whenever you have the product terms in there. Yeah. Other stuff? This is where I sweat. Okay. Well, hey, thanks a lot. I really appreciate it. And really, any questions, if you're an introvert, send me an email. All right. Thanks. All right.